Dear ladies and gentlemen, esteemed guests, my name is Péter Rőthy-Gruber, and it is a great honor to be here today and have the opportunity to share my presentation with you. My interest in science started with moments like these: laboratory practices, inspiring lectures, and memorable discussions. I would like to thank the National Academy of Scientist Education for making these opportunities possible. Experiences like these gave me the confidence to take part in the International Chemistry Tournament. I was fortunate to be selected for the Hungarian team, and last August we participated in the international round. This chemistry competition follows a format based on academic debates stemming from open-ended problems. Students have to present their solutions and defend them from other participants, forming the core of the tournament. Solving an open-ended problem is quite similar in nature to tackling a real scientific problem. You start by analyzing the scientific literature on your subject. The application of the acquired concepts then leads you to an original idea that can be used to construct your own experiments. Theoretical reasoning ensures that your solution is well-founded, while presenting your findings in a clear and structured way is essential for others to understand your work. But what does this look like actually in practice? During the competition, I encountered two tasks, each requiring a different way of thinking. In the first one, the solution could be tested and verified experimentally, whereas the second problem was purely theoretical and had to be supported by reasoning. In my presentation, I will explain the thought process behind these tasks, starting with the first. The exact requirement was to propose a protocol to measure lead in tap water and determine whether a water sample is safe to consume, all the while using only equipment and materials available in a school chemistry laboratory or pharmacy. First, you have to understand the problem. Because of its toxic effects, lead poses a serious health risk, and there is no level at which it is truly safe. So measuring the highest possible concentration is essential. The question was, how can this maximum be detected? And in what form is lead actually present in water? I found two key points. Sampling without flushing the tap captures the highest accumulation, and acidifying the sample ensures that all lead is present in only ionic form. Based on my findings, I chose a reagent that forms a colored complex with lead called xylenol orange. The intensity of this color is proportional to the concentration of lead, so it can be used for its measurement. Under the right conditions, this method should work. But there was one thing I was still unsure about. Can it detect such low concentrations? I needed a way to increase the sensitivity. I have to admit, with my first approach, it didn't work. I tried to filter the sample through an improvised solid phase extraction setup and carry out the reaction directly in the column. It was a reasonable idea, and it was based on literature, but in practice, it failed. The cellulose didn't bind the lead ions, and the reaction with the reagent didn't proceed as expected. I was disheartened. I had to start again. In the end, the right solution turned out to be much simpler, but only after further reflection. Instead of trying to isolate the lead, I concentrated the sample by evaporation. This increased the concentration of lead to a level that my method could reliably detect. At the same time, a masking solution prevented interfering ions from affecting the measurements. With this, I could finally move on to the next step. Since I couldn't use any specialized equipment, I had to find an alternative. So I built a spectrophotometer analog using readily available components, essentially a smartphone and a cardboard box. By capturing images of the samples, I could extract the color intensity and use it to calculate absorbance for quantification. With this method, I was able to obtain reliable quantitative results. The calibration curve indicates a clear linear relationship between the concentration and the absorbance, confirming that the method works as expected. Even more importantly, the selectivity was sufficient to capture concentrations as low as 0.2 milligrams per liter, all without specialized equipment. In the end, This approach proved both simple and effective, relying on experimentation, testing, and adjustment. The second problem I faced, however, was fundamentally different. My task was to identify the red pigment used by Van Gogh in his painting Irises and this degradation process, and construct a synthesis route for this pigment from the most likely degradation product. Referred to as geranium lake, the red pigment present in the painting consists of an aluminium eosin salt. Under exposure of UV and visible light, it breaks down into multiple products, the most prominent being DHBA. This is the chemical from which I began the synthesis process. Here you can see the painting in its present form with blue flowers. And here is the reconstructed version with purple flowers. To tackle the problem, I used a retrosynthetic approach. I broke down the target molecule into simpler precursor structures until they resembled known molecules. By consulting databases and literature, I was able to construct a synthesis with feasible steps. But there was one part that proved less straightforward. I had to turn DHBA into phthalic anhydride. This step required the oxidative cleavage of the diaryl ketone, but I couldn't find an exact literature precedent. So I turned to an analogous reaction, which is a common approach in organic chemistry. Since the two molecules share a similar structure, it is reasonable to assume that the two reactions behave similarly. A proposed mechanism was also used to further justify this step. For the next steps of the synthesis, there were many available options, from which I selected a compatible sequence of reactions based on the formation of fluorescein. First, phthalic acid was dehydrated under heating and in the atmosphere to yield phthalic anhydride. This then, in conjunction with isocyanates, produced fluorescein, the skeletal structure of eosin. The bromination of this molecule produced us our final product, eosin Y. However, the synthesis is not yet over. For artistic use, eosin Y was precipitated as a monometallic aluminum salt, forming the pigment used by Van Gogh himself. With this approach, I was able to solve the task and propose a plausible pathway for this pigment molecule. Beyond the chemistry itself, this competition had a broader impact on how I approach problems. I became part of a team, and we faced challenges together and learned to truly collaborate. This also taught me how to work under pressure and adapt to the present situation. I also realized that solving a scientific problem is not a series of clear steps. In reality, it looks much more like this. At every stage, you are asking more and more questions, and very often, the answer is that you have to rethink and start again. This is exactly what happened in both of my problems. Results didn't come from following a path blindly, but from questioning it along the way. I would like to once again thank the National Academy of Scientist Education for providing these opportunities. I would also like to thank my team and mentors. I feel very fortunate to have been part of such a supportive and dedicated team. And last but not least, I am truly grateful to my teachers, Bence Farkas-Szabó and József Baranyai, whose guidance and encouragement were fundamental throughout this journey. Thank you for your attention.
Thank you so much, Peter, for this excellent presentation. So now you'll get your award. And while we are doing that, can I ask the two teachers mentioned, Bence Farkas-Szabó and József Baranyai, to join us on the stage as well? Thank you so much.